Hello, Flat Earth researchers, debaters and debunkers. Horizons is probably one of the most contentious topics of discussion when it comes to attempting to define the shape of our Earth and how we see it. We are commonly led to believe or interpret the horizons we see in front of us as being due to us living on a globe Earth. However, even this definition has not been clearly defined. We are presented with a mixture of conflicting interpretations as to what the horizon is when we look straight ahead across the surface. On one hand, we are told that the surface is curving away from us and that gaining more height above the surface means we are looking down further along that curve. However, this doesn't make sense if we are seeing a horizon just a short distance in front of us, yet we cannot see an equivalent bend or curve in the horizon on the horizontal from left to right. The view of which we have is often much wider in miles or kilometers than what we can see in front of us. So this is a conflict in itself. But one of the other ideas that is an interpretation of perspective is that we are seeing this hump or bulge of curvature rising up in front of us. Of course, we know this isn't the case. We just have to compare how we look across a flat surface and see that the horizon or the apparent end of that surface will appear to rise up to eye level. And we can prove and demonstrate on pretty much any scale that these optical phenomenon are what happens when we gain height above a flat surface. Here we see a road that's about 600 meters long, less than a kilometer, and it's flat. And as we go up above the flat surface, we see the horizon on the surface going off into the distance, and as we come down lower to the surface, we see the horizon on the surface coming closer to us, and the rest of the surface beyond that still there in our vision, but mirroring everything else above it. We often see this optical illusion of an apparent horizon on the surface when we look across bodies of flat water, when in fact we can see the surface extending quite far beyond where the apparent horizon is, with this boat appearing to be floating in midair, when it is in fact on the surface and on the real horizon, exactly where it should be for the observer at their eye level if they are looking directly ahead. There is no refraction involved here. We simply have mirroring on the surface beyond the apparent horizon up to the real horizon where the boat is sitting. That mirroring of the sky makes the surface appear the same color as the sky, and so we seem to have a dip in the horizon. So it is this illusion of a horizon that appears to be below the eye level of the observer, which anti-flat earthers will use in an argument to say that we see a horizon that drops below eye level, therefore concluding that as we rise up above the surface, we must be rising over a ball that is dropping away from us, when in fact the reality is that the horizon does rise to the eye level of the observer. The surface and the sky appear to meet at eye level, but depending on how high or low we are above that surface and how far we can see, we will eventually reach a point where we lose the detail of the distant surface because the angle at which the light is reflected off that surface and reaching our eyes is too shallow for us to make out any detail on the surface, and instead we see mirroring of the sky above the surface. We can see that a little more clearly in this photograph of a ship on the horizon taken from a relatively low perspective across the flat surface of the water. We have an apparent horizon on the surface quite close to us because of our low perspective, and then mirroring on the surface beyond that up until the actual horizon where the ship is sitting. And any other ships beyond that one would still be sat on that same horizon line. They would just become more distant and apparently smaller over distance. This real science of perspective is a simple, repeatable observation that can be made on any scale when changing our height above a flat surface. From a low perspective, this toy car placed in the middle of a table appears to sit on the horizon. Anything beyond the car would also be sitting on the horizon from this perspective. But as we gain height above the flat surface of the table, that surface appears to extend beyond the car. This photograph, taken from a relatively low perspective across the water, shows the same thing, with a ferry in the foreground but on the horizon, which is close because we are quite low to the surface, as well as an island in the distance which is also on that horizon. We know that if we rise up above this flat surface, we will then see more of the surface between the ferry and the island. This has nothing to do with looking down any curvature. It is a simple scientific fact of perspective when looking across a flat surface. And if we gained even more height while looking straight ahead, we would see the surface of the water stretch beyond the island in the distance without having to look down as the surface rises up to our eye level. We can see from this photograph that the horizon is not the beginning of any curvature. At the horizon, the water remains level and flat, far off into the distance. The boat on the left is closest to us, we can tell because it's just below the horizon. But on the right we have a boat that seems to be sitting on the horizon where the alleged curvature would begin. But way off in the distance, in the middle of the photograph, we have an oil rig, I believe. That is much farther away but still sitting on that same flat horizon. So this photograph in itself tells us that we have flat water extending out from us all the way to that oil rig. So basically this horizon line that we see on the surface a short distance in front of us is not the top of any bulge of curvature, nor is it the start of any curving down across the surface. That surface of water obviously, observably, continues to be flat as far as we can see. This photograph, taken from a slightly higher vantage point, nicely illustrates the laws of perspective over a flat surface. As we are higher above the surface, we see boats nearby and far away that are still not on or beyond the horizon. Yes, we might have to look down to see those boats, but we look straight ahead to see the horizon at eye level. But what we can see when we look down is a lot more of the surface between the vessels is visible to us from this vantage point, whereas if we lower our perspective and get close to the surface, then all of these boats would appear to be on the horizon at a short distance in front of us. It's got nothing to do with any alleged curvature. It is simply a result of changing perspective while looking across a flat plane. While we're at it, let's clear up this misunderstanding that a photograph like this, with just the mast of a ship poking up above the horizon, means that the ship has gone below the horizon due to curvature. This is simply not the case, and our eyes alone can tell us this. We don't need to do any measurements to work this out and see what's actually going on. The only way we can take a photograph like this is to get very low to the surface of the water and then zoom in on the horizon. We can see a lot of detail all across the surface, and we can tell by this that the horizon is very close, meaning the photograph was taken from a very low elevation. We see the same kind of detail on the surface in this shot, telling us that we are really not looking very far across that surface until we get a horizon, which of course on something like the sea is caused by the highest wave between us and the ship. So this gives us an unnaturally short cutoff. And when we look at these kind of shots, we know instinctively it's not curvature. We get this kind of unnatural difference or vast gap between the horizon in front of us and the ship much, much farther away. So we end up with this kind of comical cartoon-like effect for a two-dimensional screen where the boat is getting smaller in apparent size as it goes off into the distance due to perspective, as we would expect. But this very close and sharp horizon makes it seem as if there is this dramatic drop beyond the horizon, not some gentle curve. So we know again that this is not the result of any physical curvature, but one of perspective that makes the horizon rise up to eye level, and that is caused by whatever is the tallest obstruction in front of us, between us and the boat. We also have to keep in mind that experiments or tests done across very smooth artificial surfaces, often indoors, cannot be compared to the conditions and the surfaces we find in nature, none of which are entirely smooth and flat. They all have bumps, ridges, dips, and of course waves. This footage, taken on a flat but slightly bumpy road, shows how dramatic that cutoff can be when we get a horizon on the surface. Here we can see multiple horizons as we rise up, and then as we come down again we see how the runner's legs get cut off by just the slightest bump on the road between us and the runners. So this also applies to views across the sea, where waves of varying height will be between the observer and the distant ship. So of course the lower we get to sea level, the greater the chance there is a wave as high or higher than our eye level between us and the distant ship. But when we get a higher perspective, then there is no dramatic cutoff. Ships here can be seen going off into the distance, with many of them on the horizon and travelling further into the distance. So when we compare the geometry that makes up the mathematical model of the spinning globe with our real-life experiences and observations, we can see and understand that our perspective has geometry, the same geometry as the alleged globe Earth, but our perspective, the way we see things, has been ignored and replaced with an imaginary curve. We are taught to interpret what we see across a flat surface as being due to curvature and the Earth moving, rather than the Earth being stationary, not curving, and everything else in the sky moving above it. Apart from the confusion over horizons, there's also the conundrum of the physics involved to have aircraft flying around a spinning globe. And this photo of a jet taking off from a moving aircraft carrier is a great example of what you have to think about when it comes to scrutinizing the spinning ball Earth and how it should or could or maybe not work. So regardless of whether the aircraft carrier is moving or not when the jet is on it, once the jet takes off from this moving aircraft carrier, it is independent of that carrier. It is now in the air, which is also free flowing across the Earth, as is the water. And we know that no matter how fast or slow that aircraft carrier is going, if the aircraft, once it's taken off, turns around and heads in the opposite direction, then it will have a much greater distance to go in order to return to the aircraft carrier as it carries on in the direction it was already going. Does this happen in everyday life when aircraft take off with or against the alleged spin of the ball Earth? Or is flying around the Earth just the same as flying across a flat, motionless plane? If it is claimed otherwise, then surely there must be some kind of scientific proof or practical examples of this. Anyway, back to horizons and perspective. I've put together a collection of photographs of seascapes with horizons and making use of perspective that we can just go through and look at without making calculations and measurements, just seeing what we see and seeing what makes sense to us just from observations and our common experience. This photograph was taken from quite high up, and so we see several ships going off into the distance below the horizon, which is relatively close because of the hazy conditions. In this shot we have a horizon in the distance which appears to be higher than the ship's deck. We know that this is not actually physically happening. This is just a result of perspective, looking across a flat surface that appears to rise up to the observer's eye level. This is a good example of perspective where we have ships below us and aircraft above us, all traveling in straight lines. But you can see that in the distance they would appear to converge at the horizon, where the surface and the sky appear to meet. We know from this photograph that the camera was at about the same height as the building in the foreground, because that building is in the center of the photograph. And then beyond that we have a horizon that also rises to that same level. And we know this is an optical illusion of perspective across a flat surface, because we know that it is not a bulge in the ocean that rises up as high as that building in the foreground. In fact, we know that if we flew off to the horizon and stayed at this height, we wouldn't eventually run into the surface which appears to be bulging up in front of us. We would just keep on going with a horizon that was always staying at eye level. The same goes for this one, taken from a relatively high vantage point. We can judge the height by comparing the towers in front of us and counting the floors up to the level of the camera, and we can see that the horizon beyond that has also risen up to eye level. Again, we know that the sea isn't rising up as high as those tower blocks. It is simply a flat surface that we are looking across. Again, in this shot, the horizon appears to be higher than the foreground, and in this particular photograph, the horizon is slightly higher than eye level because the focus is on those tables in the foreground, and so the camera is slightly tilted down. This one's interesting because the camera is tilted to follow that path down to the sea, and so we have a horizon that is above eye level, and we know then that the camera is not looking straight ahead. This is a frequently photographed lighthouse, and we'll see in the next few images this same lighthouse taken from different vantage points, showing different perspectives, and so it's worth just looking at what the horizon does in each of those shots. Here we can see it's pretty much at eye level. And if we keep the horizontal line indicator there throughout these shots, we can see more easily the kind of angle that the camera was pointing when these shots were taken. This one is obviously pointing upwards. This is a very dramatic one of a different lighthouse, where again we see the distant horizon rising up to the same level as the rock face. which is, again, something we know is not physically happening. It's just an optical illusion. And in this one, we know the camera is angling down from a high vantage point, and we have a horizon that is higher than the camera's eye level, but we can see that it appears to be as high as the lighthouse, which is simply a result of perspective, again, across a flat surface. And in this one, we know that the camera is pretty much at the same height as the top of the lighthouse. And again, we have a horizon in the background that is at that same height. This shot shows us that conditions play a large part in the distance we can see to the horizon as well. Again, the horizon is at eye level, but we are not seeing very far at all just because of this cloudy weather. Perspective is easily distinguishable in this one, with the buildings appearing to taper off into the distance towards that horizon, which again seems to be as high as some of the lower floors of the buildings in the foreground. Another beautifully flat landscape from a very high vantage point, with a horizon that appears to be even higher than those tall towers in the foreground. In this one, we know that the camera is at about the same height as the top of the cliff on the other side, and we have the horizon in the background rising up to that level. Here's another photograph taken from a high vantage point, and we can see again that the horizon in the distance seems to be as high as the buildings in the foreground. But this is simply, again, perspective at play, putting the horizon at the camera's eye level. This one plays with perspective again, and if we follow or trace those lines of perspective, they meet at the horizon. In this one, the camera is tilted down to get more of the foreground into the shot as the sun sets or travels away across the flat plain. This final photograph really says it all about horizons and proves that the horizon does in fact rise to eye level, regardless of our height. I can't remember who did this experiment, but I will put a link in the description if I find out. But the intention of the person taking these photographs was to very accurately measure the heights at which he was taking the photograph and the building in the foreground, and he made sure that the camera was looking straight ahead and level. So of course in the background we see a horizon that rises up to that eye level, the same height as the building in the foreground. We do instinctively know and recognize that the water in the background isn't physically rising up to the height of that building in the foreground. We know that we are not looking down a curve. We know that we are looking straight ahead, and when we do so, the horizon rises up to eye level. And therefore, perspective is the imaginary curve. Thank you very much.